Welcome to a deep dive into
Oh,
the world of viscous free-surface flows.
okay.
We're going to be looking at a PhD thesis today.
Sounds good.
But don't worry, we're not going to bore you with all the super technical details,
Okay.
just the fun stuff.
Awesome.
Essentially, we're talking about flows where one of the fluids has almost no resistance to shear stress,
Right.
like air.
Okay.
And the tiny bit of viscosity in the other fluid,
Yeah.
like water,
Okay.
can really change how things behave.
It's amazing how much of a difference that tiny bit of viscosity can make.
Yeah, so like what are some examples from the real world where this matters?
Well, this thesis looks at a whole bunch of cool examples, like how dewdrops cling to leaves.
Oh, wow.
It's all thanks to that little bit of viscosity.
That's neat.
And there's more. They also explore the physics of a water drop hitting a mosquito.
No way.
Yeah, and how mud volcanoes erupt.
Yeah.
And even how the viscosity of a liquid affects the pop of a bursting bubble.
Wait, the pop of a bubble?
Yeah.
Really?
Oh, yeah. It's all connected.
So these flows are like everywhere then?
They really are. And understanding them can help us design better surfaces, control liquids more effectively, and even unlock the secrets behind some natural phenomena.
Okay, I'm definitely intrigued.
Great.
So let's jump into the research.
Sounds good.
Chapter 1 focuses on something called the second force peak in drop impacts.
Right. What is that? So you know how a water drop can bounce right off a superhydrophobic surface?
Yeah, like those water repellent fabrics.
Exactly. Well, scientists were measuring the force involved when a drop hits these surfaces, and they found something unexpected, 2 peaks in the force instead of just 1.
2 peaks.
Yeah.
Huh. I would have thought just one when it first hits.
You'd think so, right? The first peak is exactly the initial splat,
Okay.
but then there's the second peak that appears as the drop recoils and forms that Worthington jet shooting upwards.
So what's causing that second peak? Is it like a mini explosion or something?
Not quite. It's all about momentum transfer as the drop recoils and that jet shoots up. There's a counter jet pushing downwards.
Oh.
It's like a tiny trampoline effect within the drop itself, and that creates the second force peak.
Wow, that's pretty cool.
It is.
But why should we care about these force peaks?
Well, understanding these forces could help us design even better superhydrophobic surfaces. Imagine fabrics that are even more water repellent, or surfaces that never get wet, even in the pouring rain.
Now that's impressive.
Yeah.
So how did the researcher dig deeper into this phenomenon?
They categorize drop impacts into 4 distinct regimes based on how the force behaves.
Okay.
It's like tuning a musical instrument. Each regime has its own unique sound.
Oh, I like that analogy.
Yeah, so you've got the capillary regime where surface tension is the dominant force, and the second peak is pretty subtle. Then there's the singular jet regime, where capillary waves create a surprisingly strong second peak even at low speeds.
Really?
Yeah, picture a tiny droplet making a massive splash.
Wait, a tiny drop making a big splash? That doesn't seem right.
Yeah, I know it's one of the surprising insights this research revealed. Then you have the inertial regime, where the force is driven by the drop pulling back in on itself, and the peak scales directly with how fast the drop hits.
Yeah.
And finally, there's the splashing regime, where things get messy, but even then, the timing of that second peak remains predictable.
So this research breaks down a complex phenomenon into these easy-to-understand categories. It's like a roadmap to understanding how drops behave.
Absolutely.
Yeah.
And this understanding can be applied to a wide range of applications, from inkjet printing to designing surfaces that can control the spread of liquids.
So we've seen how these drops make a splash, but Chapter 2 takes a different angle.
Yeah.
It asks, when did the bouncing stop?
Right.
I mean, we've all seen those cool videos of drops bouncing endlessly on super hydrophobic surfaces.
Yeah.
But they don't really bounce forever, do they?
No, they don't. Eventually, they stop and stick.
So what's going on there?
Well, the culprits behind this are gravity and those viscous forces we've been talking about. They work together to steal the drop's rebound energy. Think of it like a bouncing ball slowly losing its energy until it comes to rest.
So is there like a point where a drop is just too viscous to bounce?
Yes, the research actually pinpoints a theoretical limit to how viscous a drop can be and still bounce off. This finding has implications for things like inkjet printing and making sure pesticides actually stick to plants.
Oh, yeah. I never thought about how the viscosity of a pesticide could affect how well it works.
It's an important factor.
Yeah.
And here's where it gets even more interesting.
Yep.
Think about a scenario where a less viscous drop might actually stick better because it spreads out more on impact.
Oh.
This means it has more contact area with the surface and thus experiences more friction.
Hold on, you're saying a less viscous liquid could actually stick better?
Yeah.
That seems backwards. Wouldn't a thicker, stickier liquid naturally adhere more strongly?
It's counterintuitive, but it highlights the interplay of different forces. In some cases, that increased contact area caused by spreading can outweigh the lower viscosity, leading to better adhesion.
Okay, that's kind of mind-blowing.
It is.
So viscosity isn't the only factor at play here. It's a delicate balance between viscosity spreading and the properties of the surface itself.
You got it. And understanding this balance is crucial for designing surfaces and liquids for specific purposes.
Now, Chapter 3 throws a new element into the mix.
Okay.
Viscous coatings.
Right.
So now we're not dropping onto a solid surface, but onto a thin liquid film. Imagine a water drop hitting a puddle of oil.
Yeah. And the behavior changes dramatically depending on how thick and viscous that coating is.
Okay.
The drop might bounce in a substrate-independent way,
Substrate independent.
meaning it acts like it's on that trampoline surface we talked about before.
Oh, okay.
Or it might become entangled with the coating's properties, leading to a whole different dynamic.
So when you say substrate independent, you mean?
It means the drop's behavior is not significantly influenced by the properties of the surface underneath the coating.
Got it.
It's like bouncing on a trampoline. It doesn't really matter what's under the trampoline as long as it provides that springy support. Ah, okay. So in this case, the drop is bouncing on the oil, not the surface beneath it.
Exactly. And the key player here is something called the effective mobility of the film.
Okay.
It's essentially a measure of how easily the coating can flow, and it's determined by the coating's thickness and viscosity. Think of it like a thick syrup versus a thin oil. That difference in how easily they flow relates to their effective mobility.
So how does this effective mobility affect the drop's behavior?
Well, it determines how much of the drop's energy gets dissipated on impact. A highly mobile film, like a thin oil, will let the drop bounce more freely. But a less mobile film, like a thick syrup, will absorb more energy, making the drop more likely to stick.
And of course, there are some counterintuitive findings here as well.
You bet. Sometimes a less viscous coating, like that thin oil, can actually make the drop stick because it deforms more and increases the contact area, leading to more friction.
It's like the coating is trying to grab hold of the drop.
Exactly. But remember, understanding this behavior is crucial for designing coatings with specific purposes. Think about water-repellent fabrics or controlling how drugs are delivered in the body.
That's fascinating. So we've seen how drops behave on solid surfaces, and now we're starting to understand how those thin liquid coatings change the game. But what happens when a drop hits another drop?
Yeah.
That's where things get really interesting, right?
You're right. That's where we head in Chapter 4. So Chapter 4 looks at drop-on-drop interaction.
Okay.
So, like, imagine a drop hitting another drop that's already just sitting there on a superhydrophobic surface.
Oh, so it's like a tiny little billiard game.
Exactly. And just like in billiards, the angle and speed of the impact can lead to a bunch of different outcomes.
So what did the researchers find in these drop-on-drop collisions?
They found 5 distinct scenarios. Sometimes the drops merge together, sometimes they stay separate, sometimes both drops bounce off, other times just one does. It all depends on like the specific conditions of the impact.
So were there any like surprising or counterintuitive results that came up?
Yeah, actually there's a great example of that in this chapter. You might think that a direct forceful hit would be the best way to get a drop to come off the surface.
Yeah.
But what they found is that a slow off-center impact can sometimes be more effective at lifting the stationary drop.
Wait, really? So a gentle nudge can be more powerful than a direct hit. How does that work?
It's all about how the energy is transferred during the impact. A slow off-center impact can actually transfer more energy to the stationary drop, which gives it enough momentum to lift off the surface. It's kind of like using leverage to move a heavy object.
Okay, so even these seemingly simple drop interactions can be pretty complex. How did they even capture all this detail? Were they using like high-speed cameras to film these tiny collisions?
They used high-speed cameras and something called direct numerical simulations, or DNS.
DNS, what's that?
It's a computational technique that allows researchers to simulate these flows in a lot of detail. It's like creating a virtual lab where they can control every aspect of the interaction.
So they could like see these collisions in a way that wouldn't be possible with just a camera?
Exactly. And the best part is the results of their simulations matched the experimental data really well.
Oh, wow.
It's like having a crystal ball to show you what'll happen in this microscopic world.
So why is it so important to be able to predict these drop-on-drop interactions so precisely?
Well, it's crucial for any technology that relies on precise drop placement.
Yeah.
Like inkjet printing, 3D printing with liquids, or even spraying pesticides or pharmaceuticals.
Right. So if you want those tiny drops to land in a specific spot, you need to understand all the forces involved.
Exactly. Now, in Chapter 5, we move from impacting drops to what happens when a liquid film ruptures.
Like a soap bubble popping.
You got it.
I have to admit, I've never really thought about the physics behind how a soap bubble pops.
Well, there's a whole area of research on that. The classic scenario is a soap film in the air. When it pops, it retracts really fast because of surface tension,
Okay.
like a tiny curtain closing.
Yeah, I can see that. And this retraction happens at like a specific speed.
Yeah, in air, it reaches a constant value known as the Taylor-Cullick velocity.
So no matter how big the bubble is, it always retracts at the same speed.
In air, yeah, that's the classical theory. But this research changes things up by asking, what happens when the film is surrounded by something else, like oil?
So the oil would create more resistance and slow it down, I guess?
Exactly. They call this the two-phase Taylor-Cullick configuration, where a water film retracts in oil.
Okay.
And they found that the retraction speed is still constant, but how fast it is now depends on how viscous that oil is.
So it's like trying to run through molasses compared to air.
That's a great analogy, but it gets even more interesting.
Oh, how so?
They also looked at a three-phase configuration where you have a water film sandwiched between air and an oil bath,
Okay.
like an oil drop on a water surface. When the water film under the oil pops, the retraction speed is still affected by the oil, but not as much as in the two-phase case.
So being totally surrounded by oil has a stronger effect than just having oil on one side. That seems a little weird.
It does, right? And that's where simulations really helped. They used simulations to actually visualize the flow and found that in the three-phase case, energy loss from friction is concentrated near the three-phase contact line.
Okay, hold on. What's viscous dissipation in the three-phase contact line?
Oh, sorry. Viscous dissipation basically means the energy loss from friction in the liquid.
Right.
Like when you rub your hands together and they get warm, that's energy being dissipated.
Okay. And the three-phase contact line.
So think of that oil drop sitting on water. The three-phase contact line is the circle where the air, the water, and the oil all meet.
Got it. So in the three-phase case, most of the energy loss from friction is happening right at that circular boundary.
Exactly. And because of that, the retraction speed doesn't depend as much on how viscous the oil is.
Oh, so it's like the energy is being channeled into one spot, and that reduces the overall impact of the oil's viscosity.
Precisely. They even came up with a new equation to describe how the retraction speed changes based on the oil's viscosity. This finding could help us understand things like how filaments relax in viscous media, and even what happens to the air film when a drop hits a surface.
Wow. So we've explored bouncing drops, drops colliding, and now these retracting liquid films.
Yeah.
What's next in our journey through this thesis?
Well, for our final chapter, we're going back to bursting bubbles.
Okay.
But this time with a twist.
I'm all ears. Okay, so we're back and ready for the final chapter in this PhD thesis.
Yeah.
You said bursting bubbles with a twist, so what is that?
So in this chapter, we look at what happens when a bubble bursts in a liquid that's not just viscous,
Okay.
but also what we call viscoplastic.
Viscoplastic.
Yeah.
Okay, remind me what that means again?
Think of things like mayonnaise,
Okay.
toothpaste mud.
Okay.
They act like solids until you put enough stress on them and then they flow like a liquid.
Oh, right. Like you can push a spoon through yogurt,
Exactly.
but it feels solid until you use enough force.
Yeah, that's viscoplasticity.
So are you saying those cool videos we see of bubbles bursting in slow motion with all those colors?
Yeah.
That could be because of this viscoplastic behavior.
Exactly. It's not just surface tension creating those patterns. When a bubble bursts in something viscoplastic, you have surface tension, viscosity, and yield stress all affecting how it breaks apart.
So what happens instead of a clean pop in a flat surface?
Well, instead of a clean break, you might see the bubble stretch into form in weird ways before it finally collapses.
Oh, wow.
It's like it's fighting back.
So is there any practical use for knowing how these viscoplastic bubbles burst?
Definitely. Think about those slow motion videos of paint splattering or chocolate syrup flowing.
Oh, yeah.
The way those fluids behave is all because of these forces.
Cool.
And if we understand them, we can control these processes in amazing ways.
So we've talked about bouncing drops, colliding, retracting films, and now these viscoplastic bubbles.
Yeah.
What's the big takeaway from all this?
Well, the main thing is that those viscous forces, they're super important in how these free surface flows behave. They affect everything from how drops bounce and spread to how films retract and bubbles burst.
And this research isn't just describing these things, it's actually explaining the physics behind them, right?
Exactly. It breaks down complex behaviors into simple categories, and it shows us how seemingly unrelated processes are actually connected.
It's like we're seeing the invisible forces that shape the world around us. And knowing this has implications for fields like materials, science engineering, and even biology.
Oh, sure.
So is there anything that this research made you think about or any questions you're left with.
Well, this thesis mostly looked at Newtonian fluids like water and oil,
Right.
but I'm curious how things would change with non-Newtonian fluids like polymers or blood.
That's a great point. It's like this research opens up a whole new area to explore with even more complex flow behaviors.
Exactly. There's so much more to discover.
Well, this has been a fascinating deep dive.
It has.
I feel like I've learned so much about the hidden world of fluids.
Me too.
Thanks for joining us on the deep dive.
It was my pleasure.
We'll see you next time for another look at some cutting-edge research.